Welcome back. In this video, I am going to talk about how to frame the differential equations. Differential equations can be formed by eliminating arbitrary constants. So what are the arbitrary constants? There are the various constants like fixed constant and the arbitrary constant. Arbitrary constants are those whose value you can change. Arbitrary constant can take any value within the given range. By using arbitrary constant, we can draw family of curves. So in today's video, I am going to form the differential equations by eliminating arbitrary constants. For example, x cube plus y cube equals to 4ax. In this equation, a is arbitrary constant. 4 is a fixed constant. It is not changing. But a is arbitrary constant. So a can have the different values. A can have different values. And by changing a, you can draw the narrowed curved or the like this. Suppose these are the two curves. One is the narrowed, another is the widespread. So this is because of change in the arbitrary constant. But the shape of the curve is not changing. Only the size of the curve is changing. So in short and sweet, the constant which is responsible to change the size of the curve and the shape remain the same is nothing but called arbitrary constant. Here, let us consider some examples. The first example, a is only one arbitrary constant. The first equation having only one arbitrary constant. Second example, capital A and capital B. There are the two arbitrary constants. In the third example, the single arbitrary constant, that is A. And in the fourth example, there are the two arbitrary constants. And in the last example, again there are the two arbitrary constants, that is the C1 and C2. If you wish to find the differential equation from this algebraic equation, then you have to eliminate arbitrary constants. Example number 1, form differential equation if general solution is given by y equals to a sin x. So what is given? Y equals to a sin x. And a is a arbitrary constant here. It is having a as a arbitrary constant. Now we have to frame the differential equation by eliminating arbitrary constant. That means we have to find the value of a. So for that I have to do the derivative. So dy by dx. I have to do the derivative. Dy by dx equals to a into derivative of sin x is nothing but cos x. So dy by dx equals to a cos x. Therefore a value is nothing but dy by dx into 1 upon cos x. So given equation, call it as a 1 and call it as a 2. Now what you do? You put the value of a in the equation 1. You put equation 2 in equation 1. We have y equals to a. A is nothing but the value of a, dy by dx into 1 upon cos x multiplied by sin x. So y equals to dy by dx into sin x upon cos x. So that implies tan x into dy by dx equals to y. We can write it more better way, tan x into dy by dx minus y equals to 0. So this is required differential equation. Thus, by eliminating arbitrary constant, we can frame the differential equations. Here I am going to help you by solving more examples and going to frame more differential equation by eliminating arbitrary constants. Obtain differential equation if y equals to a into e raised to 2x plus b. Solution: y equals to a e raised to 2x plus b. Differentiating with respect to x, dy by dx equals to a into e raised to 2x into 2. Derivative of b is 0. Therefore, dy by dx equals to a into e raised to 2x multiplied by 2 implies a into e raised to 2x equals to 1 upon 2 into dy by dx. Call it as a equation 1. Call it as a 2 and original one as a 1. Now putting 2 in 1, we have y equals to half dy by dx plus b, because there are the two arbitrary constants. Only one till now we have removed, we have eliminated, but the another arbitrary constant b is left. We have to remove even that. So we kept the equation 2 in 1. Now we have to do differentiate once again. So differentiating again with respect to x. Therefore differentiation of y with respect to x equals to differentiation of half dy by dx plus b with respect to x implies dy by dx equals to half d2y by dx2 plus 0. Therefore, what is the final answer? The final answer is nothing but 2 into dy by dx minus d2y by dx2 equals to 0 is required solution. Form the differential equation if y equals to ax square bx plus c. We have y equals to ax square plus bx plus c. There are the three constants. There are the three arbitrary constants. So number of arbitrary constant will decide order of differential equation. Implies we have to do the derivative 3 times. Now first of all, dy by dx equals to a into 2x plus b plus 0. Differentiating once again, we get d2y by dx2 equals to 2a plus 0. Now the last arbitrary constant a is left, so we have to do the differentiation once again. So d3y by dx3 equals to 0. The purpose of forming the differential equation, the main idea of forming the differential equation is eliminating arbitrary constants. Finally, we should not see any arbitrary constant in the equation. So d3y by dx3 equals to 0 is required solution for given general expression, that is y equals to ax square plus bx plus c. Form the differential equation from relation y square equals to 1 minus ax square upon b. Solution: this can be written as y square equals to 1 upon b minus a upon b x square. Now there are the two arbitrary constant, one is the a, another b. We have to eliminate them, and so what you can do here is a upon b, so we can say let a upon b equals to c. Therefore we get y square equals to 1 upon b minus cx square. Now differentiating with respect to x, we get 2y dy by dx equals to 0 minus c into 2x 2y dy by dx equals to minus 2cx. 2 to get cancelled both sides. Therefore, we get here minus cx equals to y dy by dx. Y into dy by dx. So call it as a equation number 2 and the given one as a first equation. Now we have to find the value of b. For that, we shall be putting the value of c in the first equation or in this equation. Even this is equals to 1. So we have here my y square equals to 1 upon b minus cx, here the plus, minus cx into x. Equation 1, this can be written as y square equals to 1 upon b plus minus cx y square equals to 1 upon b as it is, plus here the in place of minus cx I can write y into dy by dx into x. So I have here y square equals to 1 upon b plus xy into dy by dx. Now the constant b has to be eliminated. For that, differentiating again with respect to x. So derivative of y square is 2y dy by dx, and derivative of 1 upon b is 0, and here we have to do the UVW procedure, the x y into derivative of dy by dx plus y into dy by dx into derivative of x with respect to x plus x into dy by dx into derivative of y with respect to x. So 2y dy by dx equals to xy into d2y by dx2 plus y into dy by dx plus x into dy by dx whole square, which can be further simplified. So we get xy d2y by dx2. This is taken to the right side. So minus 2y dy by dx plus y dy by dx plus x into dy by dx whole square equals to 0. So we get xy d2y by dx2 minus y dy by dx plus x into dy by dx whole square equals to 0. This is required differential equation. From the differential equation, if x upon a plus y upon b equals to 1, solution here is constants are in the denominator. So to get remedy from denominator, what I can do, let 1 upon a equals to c and 1 upon b equal to d. In this way, we get rid of denominator, that is a cx plus dy equals to 1. Now it has been converted into very suitable form. Now differentiating with respect to x, so we get c into 1 plus d into dy by dx equals to 0. Differentiating again with respect to x, we get 0 plus d into d2y by dx2 equals to 0. After that, we get here d into d2y by dx2 equals to 0, which can be written as d2y by dx2 equals to 0 upon d implies d2y by dx2 equals to 0. This is required differential equation. Example number 6, form differential equation if y equals to c1 plus c2x into e raised to x. Solution: first of all, y equals to c1 plus c2x into e raised to x, call it equation number 1. Differentiating with respect to x, here we apply the product rule, dy by dx equals to c1 plus c2 into derivative of e raised to x, product rule of derivative, product rule of differentiation, so e raised to x as it is, and differentiation of c1 plus c2x. Now dy by dx equals to c1 plus c2x into e raised to x plus e raised to x into c2. Call it as a 2. Put 1 into, we get dy by dx equals to y plus e raised to x multiplied by c2. Call it 3. Now differentiating again with respect to x. So we get d2y by dx2 equals to dy by dx plus c2 e raised to x. This is called 4. From third equation, we get c2 e raised to x equals to dy by dx minus y. So implies d2y by dx2 equals to dy by dx. Now in place of c2 e raised to x, so we put this value. So we get dy by dx minus y implies d2y by dx2 equals to 2 dy by dx minus y, which can be simplified d2y by dx2 minus 2 dy by dx plus y equals to 0. This is required differential equation of this. On the differential equation, if y equals to a into cos of log x plus b into sin of log x. Solution: y equals to a into cos of log x plus b sin of log x. Differentiating with respect to x. First of all, call it as the equation 1. After that, differentiating with respect to x. So dy by dx equals to a minus sin of log x upon x plus b into cos of log x upon x. So x into dy by dx equals to minus a sin of log x plus b cos of log x. Differentiating again with respect to x. So differentiation of x into dy by dx with respect to x equals to differentiation of a sin of log x plus b cos of log x with respect to x. Here product rule, x into d2y by dx2 plus dy by dx dot 1 minus a cos of log x upon x minus b sin of log x upon x, x into d2y by dx2 plus dy by dx equals to minus common a cos of log x plus b sin of log x. Call it equation number 2. Now putting 1 into x square into d2y by dx2 plus x dy by dx equals to minus y, implies x square d2y by dx2 plus x into dy by dx plus y equals to 0. This is required differential equation. So this is the way we form the differential equations. I hope now you got an idea, a rough idea how to frame the differential equations. So differential equations are formed by eliminating arbitrary constants, and the arbitrary constants are eliminated as per as the given equation. There may be the 2 variables, there may be 3 arbitrary constant, 4 arbitrary constant, depends. So more the number of arbitrary constant, more the equation we need to frame, and we need to frame the differential equation. I have to stop my video here. Meet you again with another topic. Till then, wish you good luck. Before saying goodbye to you, I would like to request you like, share and subscribe the channel. Wish you good luck. All the best.